You ever stop and think about what's really going on inside your computer? I mean, right now, you've probably got music playing, a bunch of tabs open, maybe a chat app pinging you. It feels like it's all happening at the exact same time, doesn't it? But here's the crazy part. Most computers have one brain, one CPU, that can technically only do one thing at any given instant. So how is this possible? What's the trick behind this grand illusion of multitasking? Well, the secret behind all of that, it all comes down to one of the most fundamental ideas in all of operating systems, the concept of a process. This is the absolute cornerstone of how your computer pulls off that magic trick, and it's exactly what we're going to dive deep into today. All right, so here's our game plan. First, we're going to pull back the curtain on that multitasking illusion. Then we'll get out our virtual microscope and look at the anatomy of a process, what it's actually made of in memory. We'll follow its entire life story, from birth to death. We'll even look at how processes form family trees and how they talk to each other. And then, to tie it all together, we'll see this whole thing in action in something you use every single day, your web browser. So let's start with that illusion, that feeling that everything's running at once. The technical term for that is concurrency. The operating system is basically a master magician. Its main trick is switching between all your different programs so incredibly fast, we're talking thousands of times a second, that to our slow human brains, it looks like they're all happening in parallel. But to pull off this trick, the OS needs a way to package up and manage each of those running programs. It needs a container, and that container, that fundamental unit of work, is the process.
Now, this brings us to a really important distinction. We tend to use the words program and process like they're the same thing, but in the world of operating systems, they are totally different. A program is, well, it's passive. It's dead. Think of it like a recipe in a cookbook. It's just a file on your hard drive like spotify.exe. It's just sitting there, not doing anything. A process, on the other hand, is active. It's alive. It's the chef, the CPU, actually grabbing that recipe and starting to cook. A process is a program in execution. You can have one program file, but you can launch it multiple times, creating multiple separate processes from that one recipe.
Okay, so if a process is a program that's been brought to life, what does this living thing actually look like inside the computer's memory? Let's dissect one. When the operating system creates a process, it has to lay it out in memory in a very specific, standardized way. At the very bottom, you have what's called the text section. This is just the program's code, the raw ones and zeros, the machine instructions that the CPU is going to execute. It's the actual text of the recipe. And here's a key detail. The operating system almost always marks this part of memory as read-only. And that's for a super important security reason. You don't want a program to accidentally or maliciously change its own instructions while it's running. That would be chaos. Moving up from there, we have the data section. This is where all the global variables live. So, say you're coding up a game and you have a variable called player score. That score needs to stick around for the whole game and be seen by different parts of your code, right? So you'd make it a global variable, and its value would be stored right here in the data section. Then things get really flexible. We get to the heap. Now, unlike the text and data sections, which are a fixed size when the program starts, the heap is all about dynamic memory. It's memory that a process has to ask for while it's running. Think about a photo editor. You have no idea how big the picture a user is going to open is. So when they open that giant photo, your program says, "Hey, operating system, I need a big chunk of memory to hold this image." That memory comes from the heap. If you've ever used malloc in C or new in Java, this is what you're interacting with. The heap can grow up and shrink down as the program needs it to.
And finally, at the very top, we have the stack. The stack is absolutely essential for keeping track of function calls. Every single time your code calls a function, a new stack frame gets pushed onto the top of the stack. This little block of memory holds everything that function needs, the parameters you passed into it, its own local variables, and crucially, where to go back to when it's finished. When the function is done, its frame just gets popped off the top. It's a last-in, first-out system, which is perfect, right? The last function you call is always the first one you return from.
So the OS lays out the memory like that. But how does it keep track of maybe hundreds of these processes all running at once? It uses a super important data structure called the process control block, or PCB. The best way to think of a PCB is like an ID card for a process. It holds everything the OS needs to know about it. So let's go back to our multitasking example. The OS decides it's time to pause your music player and give your browser a turn. It meticulously saves the entire current state of the music player, what instruction it was on, all the values in its CPU registers, and stores it all in the music player's PCB. It's like a perfect snapshot. Then it grabs the browser's PCB, loads its save state back into the CPU, and says, go. This whole act of saving one state and loading another is called a context switch, and it is the core mechanical action that makes all of modern multitasking work.
All right, so now that we know what a process is made of and how the OS keeps tabs on it, let's follow a process on its journey. Every process goes through several distinct states, from the moment it's created to the moment it's gone. We call this the process life cycle.
It all kicks off in the new state. This is just the OS doing some initial setup. Once that's done, the process doesn't start running right away. Nope, it moves into the ready state. Think of this like a queue of people waiting to get through a single turnstile. They are all ready and able to go, they're just waiting their turn. When the OS scheduler finally picks our process, it transitions to the running state. This is the only state where the process is actually doing work on the CPU. But what if it needs to do something slow, like read a file from the disk? It would be a total waste to let the CPU just sit there and wait. So the OS moves the process to the waiting state. While it's waiting, another process from the ready queue gets to run. As soon as that file is read, our process moves back, not to running, but back to the ready queue to wait for its next turn. And finally, when it's all done, it enters the terminated state, and the OS cleans up all of its resources.
You can picture this flow, right? A process gets admitted to the ready queue, the OS scheduler dispatches it, and it moves to the running state, getting its precious time on the CPU. Then maybe an interrupt hop ends, or it needs to wait for some I/O, so it gets moved to the waiting state. This lets another process get dispatched from ready to running. Once the wait is over, our original process goes right back into the ready queue. A single process will bounce between ready, running, and waiting thousands and thousands of times before it's finally done.
So who is making that critical decision? Who decides which process in that big ready line gets to go next? That is the job of the OS scheduler. You can think of this scheduler as the traffic cop for the CPU. It looks at all the processes lined up, and using some kind of algorithm, it picks one and waves it through to the CPU. The entire speed and feel of your computer really depends on how good a job this scheduler does. Okay, we've got a handle on what processes are and the lives they lead. But where do they come from in the first place? Processes don't just pop into existence. They have to be created. And this leads to a really cool, organized structure inside the operating system. On systems like Unix and Linux, every single process is created by another process. This forms a hierarchy, basically a big family tree. The creator is called the parent, and the new process is the child. And if you trace that tree all the way back to the trunk, you'll find one special process, usually called init or systemd, that the OS kernel itself starts when you boot up your computer. Every single other process you see running is a descendant of that one original process. It's a great way to keep things organized. When a parent process ends, for example, the OS knows it needs to take care of any of its orphaned children.
Now, different operating systems have different philosophies on how this creation happens. Unix has this really elegant two-step dance. A parent process calls a system call named fork, F-O-R-K. What fork does is create a new child process that is an exact clone of the parent. It has a copy of all the parent's memory and everything. Then, that new child process will usually immediately call another function, exec, E-X-E-C, which tells it to replace itself with a whole new program. So the pattern is always fork, then exec. Windows is a bit more direct. It has one system call, create process, where you have to tell it right up front what new program you want to run. It just combines those two steps into one. Neither one is better, they're just different designs.
By default, processes are like little isolated islands. The OS builds strong walls around them, so one process can't just reach into another one's memory and start messing with its data. And that's a good thing. It's for security and stability. But what if they actually need to work together? What if they need to cooperate on a problem? Well, for that, they need a way to talk to each other. We call this inter-process communication, or IPC. And why is IPC so important? Well, for a few big reasons. First, information sharing. Maybe one process is gathering data from a sensor, and another process needs to display it. Second, for computation speed up. You can take a massive problem, break it into tiny pieces, and have a bunch of processes work on them all at once in parallel. And third, for modularity. Instead of building one giant monolithic program, you can build a system out of several smaller, simpler processes that each do one thing well and just talk to each other. So how do they actually talk? There are two main models. The first is shared memory.
Think of this like a shared whiteboard in an office. The operating system sets up a special region of memory and gives 2 or more processes permission to access it. After that initial setup, the OS steps out of the way, and the processes can read and write to that whiteboard directly. It is blazing fast. The only catch is, the programmers have to be really careful they don't both try to write on the same spot at the same time. The other model is message passing. This is more like passing notes in class through a mail carrier. One process bundles up its data into a message and hands it to the OS kernel. The kernel then delivers that message to the other process. It's a lot easier and safer for the programmer because the OS handles everything. But it's slower because you have the OS acting as a middleman for every single message.
Okay, I know that was a ton of theory. Let's make this all real and tangible with something you are literally using right now to watch this: your web browser.
This is the perfect example of the process model in action. In modern browsers like Chrome or Firefox, every single tab you open is really its own separate process. Why would they do that? One word: reliability. Modern websites are basically complex applications. If a buggy script on one website causes that tab to crash, the OS can just terminate that one process. And because it's totally isolated from the others, your other tabs and the main browser itself just keep on running. It doesn't bring down the whole ship. This is process isolation being used as a powerful tool for building stable software.
So let's just bring it all home with this one thought. A process is a program that has been brought to life by the operating system, given a home in memory to live in, and given a turn to run on the CPU. It really is that fundamental unit of work, the key abstraction that lets our computers create that beautiful, powerful illusion of doing a million things at once. But that leaves us with one final hanging question, doesn't it? If every tab is its own process and the CPU can only truly do one thing at a time, how does the OS decide which tab gets to run? And for how long? How does that traffic cop make its decisions? Well, that is the magic of CPU scheduling, and it's exactly what we're going to unravel in our next explainer.